Okay, so we have some people coming in right now. We're going to give it a couple seconds to make sure everyone has time to log in before we actually start the presentation. We apologize for the 30-minute delay. We hope that you saw the message this morning. So we had some really popular meetings before this one also, so we had to push it back a little bit. But we'll just give it a little bit of time and see people come in. While we wait, I'll just, this is basically the last day this week of it's the last day of the first official week of the marketplace. I want to thank everyone for their support. It's been a really good week. And I hope I'll see you this afternoon for the other presentations and also tonight for the poker game. And next Monday for the draw to know who won the attendee draw. So that's about it. And you'll be able to see all the sessions online as we speak. So now we can start with this session. After I thank, of course, Quanix, our presenting sponsor. So Al, why don't you introduce us to your guest today?
Yes, our guest today is Arman Mottaghi. He's the CEO and co-founder of Lambda Science, a local social purpose firm on a mission to deliver new energy modeling and analysis solutions to the part-time residential sector. Lambda has a flagship product called StepWin. It's a software package that improves the energy performance of home designs without an impact on the construction budget. Arman is selected as a 30 under 30 by BC Business, and he's also a board director of the BC Sustainable Energy Association. So the BC Sustainable Energy Association has been a key player in the BC's path towards a sustainable future. So Arman, we're glad to have you with us today. And you and I have had several conversations about StepWin. And I think it's such an interesting product, and it seems to be playing an increasingly valuable role for builders who want to build cost effectively to the higher levels of the BC Energy Step Code. So I think and also, it seems that because of how you've designed StepWin, it actually provides a lot of value to builders in picking the most cost-effective path, but it also tells us a lot about the value of windows in terms of achieving performance-based energy goals under the building code. So look forward to having you tell our members here why builders are choosing high-performance windows as a cost-effective option under the BC Step Code.
Good morning, Al. Thanks so much for the great introduction. And yes, I think you hit the nail on the head. Very, very thorough points there. And yes, I think today what I generally want to talk about is, first of all, give a background there, because I think your audience is more like in a national level. Give a background there about the BC Energy Step Code. Also, I want to talk about how that performance base basically turns into building science principles, how the heat is really moving in the building, and why that matters to know it, and the staples of a design that would work with these new codes. I'm also going to talk about two case studies today in Vancouver and Kelowna. I put these two because I thought one of them is a success story and one of them is actually a story of caution, or maybe not a success story so much. And I wanted to highlight why the conversations that you and I have had and why the work of Fenestration Canada is so very important in making sure that the market is directed and enough options are available out there, or the communication about it is out there, because we will see a case that perhaps Windows could have played a very big role, but that has not happened. So I want to start with some introductions about the BC Energy Step Code, if you're okay with that, Al.
Sure, yes.
Yeah, so the BC Energy Step Code, to put it in short, is a 5-step program. And this program essentially tries to get all of the buildings, all of the new construction, in British Columbia to net zero ready by 2032. The plan is that every few years, the minimum for the code would go up, and until we reach the step 5, which is the best one. And then we basically stay there as a top performer. And this is for new construction. For renovation, there are plans, but nothing has been solidified yet. And well, I'm in the national landscape, I believe there are some regulations that are being put together, the tiered code, which has a somewhat similar structure to this process, and I think has definitely the same intent. But essentially, these are very aggressive codes, right? The reason we have this timeline of 10 years or so from now is the homes they need to take generational leaps towards better energy efficiency. The hairdryer you see in this photo is one of the analogies for a high performance building, that you should be able to heat it up with a hairdryer if you get to the passive house level of performance. So moving to the BC's landscape. So the Vancouver Economics Commission helpfully gave us an idea about where the market is heading with these huge leaps in the construction. I think we could expect to see similar patterns overall across Canada. As you see, they have identified the biggest market enabler for these changes to be fenestration products. So I think there are about $2 billion of growth is projected in this space. They have a really great analysis of $1.8 billion market value that they're projecting. There are some engagements there and some really good numbers about the VEC's work. I don't know if this can be extrapolated to all Canada, but I think it's definitely worth taking a look at and kind of seeing the opportunities that these step code in BC and tiered code in Canada is providing. But
so if I could just if we could just go back a slide here, go back to the previous one.
Yeah.
So I think the point here was, Arman, with the Vancouver Economic Commission, is that they're saying that the step code is going to generate new market opportunities, and the so you see everything from drain water, heat recovery, HVAC, heat recovery, insulation products, but they're anticipating that the biggest you might say area of growth, economic growth, will come in the area of windows.
Yes.
And I suppose this in a way is telling us that their analysis assumes that windows performance is going to be critical to achieving these step code targets, and that investments in windows are going to rise. So this is going to be increase in economic value that is projected as the step code moves forward.
Absolutely.
So I think the idea here was to help the various sectors appreciate that the step code was going to lead to increased economic activity in these various sectors of the construction industry, with the largest amount of business, let's say, growth coming in the windows area. So
absolutely, 100%. And I think it really, what the case studies that you're going to look at is going to highlight that the windows are the main drivers and enablers of these changes. Now, Al, I have a question, and I want to ask it from you, and that is about this growth in the market that you highlighted. I'm wondering if you wanted to assign most of this growth to one of the two pictures you see here. Which one would you choose as being kind of the front of the high performance movement?
I think I have previously seen this question before, so I'm going to, now that I know the answer, I'm going to answer it the way I answered it the first time. I'm going to say the buildings on the right, that the large building market will be the main focus.
Yeah, so the large building market is definitely an area that is being actively worked on, and it's also under growth because of the densification in the urban landscapes. However, the left one, which is the smaller residential buildings, are a higher area built across Canada. They are also, having a lot of new spaces being added. And in the meantime, they have bigger challenges than the bigger construction in terms of streamlining the processes. So when we look at the total area of buildings built all across Canada, we see that single family homes and row homes, these smaller buildings, are having the largest total area of built across different sectors. But the cost of building one instance of that building, one archetype of that building, is the lowest amongst all of the other archetypes. And then we get to the high-rise apartments, which have the least amount of total area built, but they have a lot of construction costs to build one. There are better margins for making and creating kind of assessments of energy and planning that. So there have been better progress with making them more energy efficient on a per unit basis. So I think that question, as you may have noticed, can be answered in different ways. But I would say that the smaller construction archetypes are definitely on the front line of improvements in terms of the construction and also the environmental impact of them. And that hasn't also been missed by the market. So looking at the old system of building code regulations, we look at something, we remember hopefully something like this, which are the illustrated guides. For example, we had them in BC, that just like the code, they look at different components in the building and they each give one rate or one minimum threshold for each of these components. So for example, when we look at the windows, we have U value of 1.8. For the walls, we have R value of 15.8. And as long as you were meeting these thresholds, these minimums, you would have been fine with complying with the code. Now, this wouldn't really work out when we look at the building science principles, and that's because the heat transfer in the buildings is rather complex. So when we look at the math of it, it seemed like at the time, and it was true, that we need to move on to a more comprehensive system. And to give an example of this, I want to show this photo of a small window in a wall that basically is telling us how much heat loss can be caused by a weak element inside the envelope. Now, looking at this, white area, which is supposed to be the wall, we have 0.25 watts per square meter of heat loss. And then for the window piece, we have 8 watts per square meter. But when we put these two together and make it into one system and calculate the heat loss for the unified system, we see that the heat loss of that small window, contribution of that small window actually is about 4 times the whole wall system. So the overall wall system has a heat loss of 1 watt per square meter. And if the size of that window changes, then we are looking at heat losses maybe much more, maybe 10 times the wall area. And that is the problem with the prescriptive codes being set in the stone in terms of the minimum code requirements. We definitely want to make a flexible system, or we work on flexible systems that look at the actuality of the building performance, not just basically the minimums that have been set and may differ from one building to another. And I think this has shown itself in the results or average house consumption in Canada. So single family homes, they are using over 120 gigajoules of energy per year. Now, if I want to put that into context, I would like to think about making pasta. Now, I'm always amazed that you put a small pot of water on the stove and it takes a very long time for it to start getting to the boiling level. 120 gigajoules of energy is enough to boil a swimming pool. And one thing that I was thinking about, Al, looking at this, I mean, I've gone through this a few times, but for this presentation, when I was looking at it, it came to my mind that actually the older window technologies might exacerbate this issue. Like I'm thinking that the sealants might fail, or some of the properties of the windows might deteriorate over time, and might actually contribute to this average consumption of buildings in Canada. Do you think that would be a true notion?
Well, I think if you went back to the back to the time of aluminum windows here
Yeah.
in British Columbia, especially, where they would be you know up until the in the 80s, you still had single pane windows being installed, and in the 90s, they upgraded to double glazing, but still in aluminum frames. Many of those products, well, many of them have been replaced because the glass failed in the units because they didn't manage water very well. But the single pane products, the weather strips wore out, the hardware broke down, and made them hard to operate. But of course, they weren't very airtight to begin with. And once their weather strips wore out, they're even less weather tight. So yes, potentially that generation of windows was a huge energy loser. Um, Definitely once, the vinyl window frames came in, it got better. But, they were glazed with double glazed glass for a while until low E coatings came in and argon gas and so on. But even a vinyl window with double pane glass and a low E coating and argon fill, it's a huge improvement over those older windows. But if you go back to slides here, even that window in the wall is losing a lot of energy compared to the wall. And to me, this slide is really significant if you stop to think about what it's really telling us, right? You have a wall that is quite energy efficient, losing, as you say here, a 0.25 watts per square meter. But just by introducing one, rather small size window, that wall now, because the window is losing so much heat, that wall is now losing 1 watt per square meter. So in other words, that window is a huge energy hole and is losing so much heat that if you averaged the area of the window to the wall, in this example, the wall is now performing 4 times worse. You know what I mean? So much heat is escaping from the window. And the bigger you make that window, as in the next example, that could be, let's say, a glass patio door or a large window. Now you're losing so much heat through that window that you could double and triple and quadruple the insulation in the wall. It's not going to make up for the heat that you're losing through that window or that glass door. And so, I think that's when you said the problem with the prescriptive building code is it makes everything a little bit better. It makes the wall a little bit better. It makes the window a little bit better. It makes the roof a little bit better. But because the window is the biggest energy hole, making it a little bit better kind of wipes, most of the improvements you've made in everything else are insignificant compared to the fact that most of that heat is still escaping most quickly through the window. So, this is the thing that I think sometimes people have a hard time wrapping their heads around, not realizing that the energy loss through the windows is hugely greater than any other part of that enclosure. And so even a small basically once you make a significant adjustment to the window, it gives you more value than adding insulation anywhere else. And so I think, this kind of slide, if people stop and think about it, this kind of focuses on why windows are so important to anything you're going to do to improve the energy performance of the home. And as you mentioned, if a typical home heats enough water to boil a swimming pool over its, if you could deliver it in 1 hour, to the swimming pool. You could boil it. I mean,
Yes,
that's a lot of energy, and
definitely.
and this is where, of course, the codes are trying to solve this problem.
Yes, and this is just for 1 year for an average home.
Yeah.
Thinking about it is mind-boggling. It's not even a poorly built, just an average home for 1 year. And there is just talks about so many low-hanging fruits and opportunities to improve on that. We are also doing some work in retrofits that I will briefly mention in the end, but it really shows us the market potential, in my opinion. So moving on to the heat transfer mechanism. So Al, I want to actually, I think what you brought up is a great segue for this subject, which is about how the heat is escaping from the building. I think you made a really great way of introducing how all of these components are working together, but in the meantime, heat likes to escape from the path of least resistance, the way academia likes to put it. So, when we talk with people, and the people who you rightfully mentioned, they're not really well versed into these building science principles. And they have a design that has considered maybe their environment, the shape of the areas they want to build. And we asked them, okay, what would you do to improve on the energy efficiency of this? Usually they go to their areas of comfort, what they see as easier to add insulation to or build better, or they go to what they think should be right, such as heat going up, like hot air going up. So they would start really focusing on the roof. Now for attics, for a lot of builders, it's really easy to blow in a lot of insulation inside the space and think that they have really helped out with the heat transfer. But then there are some other areas that may not be their comfort zone. I put window and boiler as one example here, but let's say they go with a low performance and low cost in this configuration. Now, based on what you said, I guess we are both expecting this building to perform really poorly.
Yes, in other words, if the builder if the first thing you do is add roof insulation and think that's going to help a lot, that might not be the best choice, right?
Absolutely. Absolutely. And in the meantime, when the costing comes and plays with this, we see that this is going to cost also a lot, because we are dealing with that diminishing return. As you mentioned, you may add a lot of insulation to the part that is already performing somewhat better, but it doesn't really address the issue. And the way we put it into context, I think you have seen this example a few times at least, and that is, imagining going skiing on a very cold winter day, but going skiing in shorts. So I'm uncomfortable, I put on a jacket. I'm still uncomfortable, I put on another jacket. And the only thing that I brought with myself are jackets. If I go skiing in shorts, I'm going to be uncomfortable no matter how many jackets I put on, because I'm not really addressing the place that the heat is being lost. And looking at this building that we have over here on the left, it's the exact same example of having multiple jackets on the roof, but not enough insulation amongst other parts of the building. But harmonizing these insulation levels, while, for example, marginally has a higher cost for the individual window, it may result in much better performance at a lower cost level, because we are evening things out. We are putting a tracksuit or a skiing onesie and going to our skiing trip, and now, even though that we are lighter and we're more comfortable, the heat is staying in because it's uniformly insulated against. And that's the case that we have been trying to realize with the work that we have been doing. We have been trying to find the opportunities of getting materials and components that work together really well. I'm wondering if there are any questions so far, Al.
There's no questions as of now.
No,
Thanks.
not yet. Yeah.
Thanks. Okay, so let's look at the performance-based requirements. We talked a little bit about them. We talked about the BC Energy step code. And another way of putting it is heat or basically heat or cool being like water in a bucket. And the bucket is representing our building insulation. If our windows or any other component in the building is a path of heat loss, it acts like a hole in the bucket. All of the water tends to escape from there. And we need to address the holes, not thickening the wall of the bucket without addressing the holes. That doesn't do anything good for us. So I think one of the pieces that comes into play is the more complexity we have as as we are trying to address the heat loss issues. Al, I was surprised and interested to learn that the center of the glass is actually performing really well for many of the windows, and the challenges appear to be around the edges. So seems like these paths of heat transfer, paths of heat loss are kind of becoming this increasingly challenging places to address in order to really get a high performance thing. I'm wondering, like, what are the performance kind of penalties or improvements amongst the frame or the spacer pieces, and how would that really contribute to the overall window performance?
Well, you know, the glass is, it happens to be today the most thermally efficient portion of the window.
Very interesting.
In the sense that it has coatings on it which can reflect heat, and so they reduce the ability of the heat to escape through the window, and so the glass product is better able to retain heat than the window frame, which has several heat loss pathways through it, but primarily it's the conduction through the frame material. And whereas the glass, you have that gap between the panes, you have a gas inside of it, which slows down the convection loop within the glass pane, and you have the heat reflective coating. So even in a double glazed window, that glass is a huge benefit. And if you add a third pane and another low E coating, you now have the equivalent of approximately 5 panes of glass in terms of thermal performance.
Wow.
In a package with 3 panes of glass. But these improvements do not extend automatically to the frame. The frame, some window systems can accommodate double or triple glazing. And so in that kind of a window system, the frame is a constant, even if you improve the glass. And so in a similar idea to the example of how much heat is lost through the window versus the wall, the part of the product that is least efficient is the pathway that most of the energy escapes through it. So initially, the thing you can do to make a window more efficient is to upgrade the glass, with more panes and low E coatings and more gas gaps. But the next challenge is to upgrade the frame and to try to make it as good as the glass, or as close as you can get to being as good as the glass, in order to close off that pathway. So I guess as you improve the glass performance, the center of glass performance, it becomes then more and more important to address the frame performance. Otherwise, you're not getting the full benefit of a more energy efficient window, right?
It is very interesting because we usually have seen the overall window performance, and it's hard to also think about the window as this also complicated hierarchy of other pieces, and how those also contribute to the overall heat loss of the window. And when I was new to building science, I would have thought that the glazing piece, the kind of transparent piece, is the biggest contributor, but what you tell me gives a better appreciation of all of the connections and pieces that goes in the window, and what a contribution each of them can have, even though they are like a very small strip or a very small portion of the overall system. So moving on to, the performance-based ideas, this is very in line with that. We want to make a insulation kind of line all around the building that keeps the interior space separated and in a very harmonized way. It doesn't matter how we get there for the most part. The important thing is that it works. And this is where the performance-based improvements really come in. So we like to split our opportunities into two parts for improving the building. One of them is building envelope and the other one is the mechanical system. So the building envelope being the roof, the wall, the window, the basement, all of the foundation pieces. And there are important things here are the stuff like making sure that they have high insulation values, as effective as possible. So in all of those components, there are paths of heat loss. It could be through the joists. It could be through very highly conductive materials like spacers. So we want to make sure those are minimum. And in the meantime, we want to make sure that each of these components are airtight. So not a lot of cold air can bypass them and get into the building. You could have the best material out there, but if you don't really work on the joints, it wouldn't work really well. Now, when we have saturated and exhausted all of the envelope potentials, then it comes the mechanical system. Now, the mechanical system is something that a lot of people really focus on when it comes to high performance buildings. But for us, it's actually a secondary approach or a secondary pathway to go, because we think that the most efficient mechanical system is the one that never turns on. And we want to give the mechanical system the least amount of reasons to turn on and compensate for the energy loss within the home by making an envelope in the first place, and windows being an important part of it. So that's the reason we see a 80-20 situation with the choices in the building, that the first 20% of the decisions we are making really yield 80% of the results within the construction. But finding the right choices is actually rather challenging, because there are all of these different components that interplay with each other. When builders go to market, they are dealing with multiple options within the market for each part of their building. And overall, those pieces are going to, together you're looking at one optimal design, but finding that resembles finding a needle in the haystack as being so hard to find the best compliant design. So usually people just try to find something that works, and finding the cost effectiveness or the really return on investment, perhaps it's better to say, on the construction cost is not optimal with a trial and error approach. So let's talk about the impact of good windows in this whole equation, in this finding this best building. I would like to think that windows could put people on different routes. Let's say we have a builder who is faced with three choices, one of them being a high performance but more expensive window, one of them being a medium performance and a slightly costlier window, and one of them is just being the code minimum. Now, with the prescriptive requirements, we would want to go for the cheapest window that meets the code. Or if the client has certain requirements, we want to go to the threshold that those requirements are met. It's not a strategy for us to exceed or meet any requirements by going higher than that. But I would like to think about these windows as putting us onto path of different systems. Now, if we pick up a window that's inherently weak, we may want to need to compensate for the weakness of the window through another envelope component or through the mechanical system. So through the heating system that's overly efficient, so that when the heat is lost, they can compensate for it in a more energy efficient fashion. But going for a higher performance window might actually harmonize our insulation much better, and put us on a path to more cost-effective solutions along the way, so that we have better systems, or easier to construct and easier to procure systems that is going to overall give us better costs for the overall building. It actually is a very important shift in the methodology of what a good window can do, or basically any component in the building can do. We are going to ask a lot more from the people who are looking for something. What are you doing in the rest of the building? And really think about the buildings as a system, how each part of them, just like a car, how each part of them contribute to another one. And that is where I think the conversation about the water in the bucket, and what you highlighted, Al, about the role of these heat paths of heat loss play inside the overall building. So moving to moving beyond this prescriptive requirements inside BC and inside the rest of Canada means that we are going to look at very specific properties for each of these components, not necessarily just going to a minimum. If you get a call about somebody wanting to purchase a window, they won't ask for a step 3 window, because there is no such thing. They would ask for something specific compared to or in accordance with what the rest of the building is doing. So before I jump into the case studies, I'm wondering, Al, do you have any points that you want to add?
No, I think the case studies will actually make the points, clearly. So.
Okay, perfect. So I want to start with the Vancouver one. As I briefly said in the beginning, there is a success story with this case study, and then there is a story about potentials with the Kelowna case study that I want to show you. But think of a typical downtown, like single-family home, building in the city of Vancouver, and this has been presented to us. Our online interface, as Al talked about it a little bit, is called the Step-In. It's a very simple tool for us to understand how that performance-based requirements they really work out. So when we talk about the step code, and also to some degree the tiered code, we need to put the design in a software to really understand where this lands when it comes to the energy steps. So our solution to that, our solution to finding really a really good compliant design, has been a Step-In, a very simple web-based interface. You go in there, you put in the specifics of your design, and it will tell you where you are when it comes to the step code. Now I'm going to use our Step-In as the tool to really show you these case studies and the items about it. But I want to quickly walk through the interface just so that we have an idea of what is being done to really get to that step, or what are the necessary inputs essentially to get to what a step this building is lying under. And hopefully that will give a better context of when we talk about improvements or the pitfalls, we kind of can highlight that better. So this is the Step-In interface. You have a ribbon on the left. Most of the energy modeling softwares that are simplified have a somewhat similar user interface, that you have a ribbon. You go from the top to bottom until you reach a place so that you can run your design. We try to make it as simple as possible by really putting the project information in the most intuitive ways. For example, we ask for your address, and that gives us an idea about your costing, thresholds, and also about your climate. Now, this is only a BC Energy step code thing, so it really doesn't extend there, but I would like to invite all of you to create an account, put a design, use our example design, or play with one design in one of the cities and see how it's affecting the code, and how going up and down in different properties gives you results. The other thing we ask is what are the general properties of the building, how many stories you have, what sort of roof or foundation you have. Airtightness is one of the subjects that we have been adding a bit. And here we are putting a very high airtightness. I want to highlight this because I don't want airtightness to be a subject of conversation here, but that does make a difference in buildings. So we asked what sort of roof you have, what sort of wall you're thinking about. I think that important and relevant to this conversation is what sort of windows you are thinking about, what sort of frame, what sort of solar heat gain coefficient, or basically low E coatings in the windows. And finally, when you provide all of that information, we give you a best combinations that we think are going to work well. So for example, here you have said, I'm considering a double glazed PVC, triple glazed PVC, fiberglass, but I'm not really considering the wood windows. You see they're kind of faded out. And then you also say that I'm considering an instantaneous mechanical domestic hot water system and a gas-fired hot water system. So we go and look at the combination of those two, and also we go and look at the combination of the foundation options with those things, and we come up with a few, I mean tens of thousands of possible ways of building this building, and we cherry pick the ones that we think are working best for you as a result. So here we have from the top to bottom, we have a number of designs that we think are very interesting. You can click on step 5. It tells you that this design has achieved a step 5 with this kind of wall and that one kind of window and this kind of roof. So you get basically a formula of what has made this design to be a step 5. Now, if you change something in the building, there's going to be a different formula for it, essentially.
Could I make a comment here,
Yeah.
Arman? So one of the things that might that our listeners might not appreciate is that what StepWin is designed to do is to let a builder put in the geometry and the location of their building that they're proposing, and then to pick options of what they would like to consider as variables. Could be picking different range of window options, mechanical systems, other things. And what StepWin, what you've mentioned in other presentations, is that StepWin can rapidly perform thousands or hundreds of thousands of simulation runs of the various possible configurations, and pick the and basically plot the results in a way that can be used to find either the most efficient design or the most cost-effective design from all the options the builder has chosen, right?
Exactly, yes.
So basically what it's doing is, let's say typically if you were designing a performance-based building, you would go to an energy modeler and say, here's my plans, here's what I think I'm going to use for windows and doors and this and that. And the energy modeler runs the model and says, oh, no, it didn't work. You're not at step 3 yet. You need to make something better. Well, let's try this. Well, let's try that. Each time, though, it's very time consuming and takes, to produce another run. And at no point are you sure that you have found the most optimal configuration. What StepWin is doing is that it actually takes the information the builder gives it, and because it has costing information in it, as well as energy performance information, StepWin rapidly goes through multiple examples and can identify the most cost-effective way to get to a performance level, or what's the highest performance level I can get with these components. Depending what question you want to ask, the StepWin does that, and you can, I guess this overview diagram shows you by the size of the disk is probably what's the most important element in this design. Is that right?
Yes. So first of all, thanks a lot for that. I was trying to move from the interface to get to the case studies, but I think that clarification was really, really important. So yeah, we definitely, like, the first thing we show people is, all of the design space. Like, all of the single options that you pointed out, all of the single design configurations, where they land in terms of construction costs versus energy efficiency. And we want to, of course, go somewhere that's the least amount of construction costs for the most energy efficiency we can get. The disk you see here, it tells you what are the costs involved with the construction. So we have the wall, being the biggest cost driver, and then the window, and then the attic. And then if you can also switch and look at the loads. So you can see that the windows are actually really having a lot of loss in the building. And that is, I think, what we are talking about. Like, we were kind of building it up to get to this point that the windows are one of the main drivers in any of the designs that you typically see. And then we also have like carbon considerations. We have heat losses and whatnot. But I think what is important here is the recipe that makes that a step 5, and that's what I want to highlight. So we kind of find you a recipe that bakes you that a step 5 or a step 4 or a step 3 home in the most cost-effective way.
So we do have a question here. Rick Solmer is asking, are the inputs for typical details of wall designs loaded for homes across Canada?
That's a really great question. We are having this right now tuned to BC. There are also some of the considerations for regional BC needs. But the ranges that we provide for the installations by default is from a simple 2x6 wall all the way to a heavily insulated passive house wall, which I think applies to most of Canada. We have some assumptions for rain screen and things that might regionally slightly change, but you can also override or put in your own assumptions for the wall and make a wall yourself if you want to.
Okay.
Yeah. All right, so diving into the case study. So we did one Vancouver case study. I'm gonna move on from this a little bit faster because I want to get to the Kelowna case. I think that's very interesting. By the way, how are we doing in terms of time?
So we still have like 12 minutes.
Okay, that's good. So in the Vancouver cases, I want to explain this graph just a little bit. So on this horizontal axis, you see energy-related construction costs. So we want to spend the least amount of money on building a home, want to save as much as we can. So we want to go to the left of this graph, but in the meantime, we also don't want to have the least amount of energy demand. So energy demand is the opposite of energy efficiency. So how much energy our building needs to warm up the home, that swimming pool example, hopefully not to that level, hopefully much less. So I want to go to the bottom left corner of this graph as much as possible. But when we look at what the average builder has done, it's in the baseline, this faint red dot you see here, it's not optimized for costing nor energy efficiency. So we gave them a few routes of going towards better costing, going towards, spending the same amount of money, but getting a better result out of it, or going towards a high performance route. So spending more money, but getting a really, really great home. And when we looked at these options, we actually realized that the key enablers in this process was going to triple glazed windows. That was the key change that they made that made everything better. It saved enough money from other places in the building. It gave us a much more solid ground to improve the energy efficiency of the building in the meantime. So I really want to highlight, I don't have a lot of time to really jump into this, but we have a 17-page case study that you can reach out to me. My contact info is at the last slide. And I would be more than happy to share it with you about all of the details that we have dived into to really come to that conclusion on this building. But what I want to talk about right now in the time that we have got is about a Kelowna case study. We went and asked around about a typical building configuration in BC. And, I think this is, somewhat reasonable portrait of that. You may want to comment on a few of these components, but generally we found that this configuration should encapsulate like the typical home that's being in lower mainland or regions beyond it. And we then took this to the Kelowna climate, and we looked at what this design is going to give us. So we looked at a business as usual case with this particular configuration. And we saw that the construction cost, the energy related construction cost, meaning the amount of cost that goes into something related to energy efficiency, is around $200,000. Now, we don't really talk about the finishings. We don't really talk about different aesthetic options. We really talk about the installations and window systems. While the operation is around $600 a year, GHG emissions is about 1 ton a year, and the step code reached is step 3. So in that 5-step program, we are kind of in the middle. On the right side, we have these 2 graphs that Ali pointed out. One of them is about cost. The other one is about heat loss of the assemblies. And windows by far are actually creating a lot of heat loss inside the assembly. So naturally, we would think that that's the way to go to improve on the design. We gave this configuration, this particular configuration, to a step-in, and we also gave options to it to improve on and see if there is another configuration which is going to get us to here or somewhere better at a lower cost. And what we saw was that step-in optimized this design, reduce the cost by doing a few things that are somewhat strange, but when you think about it, it doesn't really work based on what it would make sense to us. It has a number of rules to play against, and it does that until it reaches the best pathways. Of course, we want this optimization to be guided by human interaction, and that's why we have a lot of options in the interface to limit the decision making to some way or direct it into another way. But generally, what happened was we went for a lower construction cost, in the factor of like $20,000-$30,000, by reducing some of or balancing out some of the roof insulation, actually decreasing the window properties from what they were to almost the code minimum. Combining the mechanical system into a combi system, and also getting rid of the heat pump, which are strange choices, but when we are really trying to cut down on the cost, that's the way that it goes on, and it was able to maintain a step 3 despite doing all of this. And one part of it could be because of very high air tightness, but it really tells us that there are many different pathways of reaching the same performance, even though they might be a little bit counterintuitive. But we didn't want to really do that. We didn't want to cut down costs at the expense of everything. We wanted a suggested design. And I was thinking initially putting this design in that the windows are going to play an important role. But I learned that the suggested design from a step-in, while it was saving, in a factor of $20,000 from the usual construction costs, rebates and everything considered, and it was increasing the step of the building from a step 3 to a step 4. So now we are getting really close to that high performance. The strategies used by a step-in to improve on that were improving the HRV system, improving the wall system by putting an insulation on the outside, and also going for an ICF foundation system, which is more insulative. So it actually started looking at anywhere that it can cost effectively improve on the design and also in the meantime save some money. And windows were not a part of this equation. So now we thought about going one step up. What happens if we want to go to a step 5? And then the windows played a very important role. So it went with a very high performance wall and a fiberglass triple glazed window, which was the best option we had available. So USI of around 0.9. Now, I don't know if somebody here would like to comment on whether better than this can be done, but that was the extent we were willing to go with it. And of course, this is the highest cost for our building, but it also exceeds gets the top highest energy efficiency level. And well, there are some rebates that could help with some of the additional investment, but I think it's very important to point out that the windows and kind of reducing the path of heat loss, the building science played a role. But I think where it really comes into perspective is that we looked at that business as usual case. If you remember, this top graph is the heat loss in the building, and the window was the biggest part of it. Now, with the step 4 home, which we didn't change the window, or step in did not recognize a change in window necessary, I just want you to take a look at what portion of the heat loss has been windows, like actually like more than anything else, even perhaps combined. But step in still did not pick better windows to address the issues because it wasn't a cost-effective route to go until we reached step 5. That you see that the overall number of heat loss is a lot smaller. The window is still the biggest part of heat loss, but that additional investment has helped us get to step 5. And if it's not clear, what I'm highlighting here is that perhaps if there were more window options available inside the interface, or the costing spectrum across different window options were different by a step in, addressing the heat loss through the windows would have been a better option rather than going for another wall or going for another HRV system. And I hope this gives you somewhat of an appreciation of what these new codes are bringing, that we have all of these components in the building, and all we need to do is to find something that's very cheap, like cheap for the performance that it brings, and we pick that up. And in this example, windows were not that until the software was essentially forced to use the high performance window because there were better things to do. So when we talk about that optimization, going from a good case to the best case, actually a lot of the money, almost half the money, went into the windows because that was something that the software could not avoid anymore. I can talk about this for hours, but just with the few minutes that we had, I hope this gave you somewhat of an appreciation of the complexities there. And we also have a new product line coming out called Properate that's focuses on really simplifying this into very understandable sheets of information being next to one another. This is one pathway and that's another pathway. We are trying to do this for existing buildings, and I think it's going to bring a lot of value for people to have a really simple understanding of the most cost-effective ways of approaching their construction. But that's where I want to leave it off. I would encourage anyone who has questions or comments or is just curious about the work that we have been doing to give me a shout. This is my email and phone number there. And I'm wondering, like, I think we are at time, but I'm wondering if there are any points you want to highlight or comments that you want to make.
At this time, well, the interesting thing is that the StepWin has the ability to do this kind of rapid analysis and compare multiple options. And the results are very specific to the climate zone the building is in and also the design of the building. So, in this case, it's showing you that, what was optimal in Vancouver was not optimal in Kelowna and led to a different outcome. And again, the interesting thing here is, and I think the potential for the future is that, if the right costing information is available for different geographic areas, this kind of a tool could be very helpful in helping, builders make the most cost-effective choices to achieve a certain performance level in a way that currently they just don't have access to that. So
absolutely, yeah. And I'm wondering that in the Kelowna example, if there were like better, like either like our database had a more cost-effective window, like a higher U value for the price of it that we had assessed, then maybe that would have given a better design than going for an HRV or for a better wall. And I
Right.
think
Yeah.
that's why, that's how the conversation that you have created, and big props to you on this very subject, really encourages our industries, like different pieces of this puzzle, to look at the potentials that are out there, and how a new improvement or innovation essentially in this area can bring in more market value to them, create more business, and in the meantime realize better homes.
Great. And so, as I think as manufacturers introduce more product lines to the market, you might end up with better pricing on some of the higher performance windows than you currently have, in your database. So
Yes.
it'll be interesting to see how that plays out.
Yes, and it can, bring in more kind of funds into the window industry than, other potential options. So I'm really excited about this interplay of different choices in the building, and seeing how that would eventually result in just better buildings overall.
Right. Yeah. Good. Well, thank you very much, Arman.
Thank you.
So thanks everyone for attending. Thanks again to Quanex, our presenting sponsor. Thanks to our gold sponsors, Screenco, Vecca, and Everlast. So what's left this afternoon, we have Dan Garnett from AdFast, who's going to tell us a little bit more about AdFast. So for those who want to join us, this is going to be at 2:30 Eastern. And after that, a little later this afternoon, we're going to have our first poker tournament. So you can tune in. Even for those who didn't sign up to play, can tune in. Thank you.
Thank you, everyone, and thanks for having me.
Thank you, everyone.